So today let's start with the chapter moving charges and magnetism with a one shot video. So coming to moving charges and magnetism, the introduction. So let's zoom in. Yeah. So Hans Christian Ørsted, a Danish physicist in 1820, noticed that a current in a straight line wire caused a noticeable deflection in a nearby magnetic compass needle. Right? You can imagine a compass needle and also imagine a straight line wire through which I am passing some amount of current. So the needle will show deflection, and that too noticeable deflection means up to a certain angle, right? And alignment of the needle is tangential to an imaginary circle which has the straight wire as its center and its plane perpendicular to the wire. So, how is the alignment of the needle? The needle is aligned tangential to an imaginary circle which has a straight wire as its center. Those straight wire is the center of that circle, right? To which the needle's alignment is tangential. Okay, and these all things are imaginary. Now reversing the direction of the current reverses the orientation of the needle. Next, iron fillings sprinkled around the wire arrange themselves in concentric circles with the wire as the center. So, as we know, here you can see in this image as well, they arrange themselves in concentric circles, right? North and south pole. This is magnetic field, right? These are magnetic field lines. They arrange themselves in concentric circles. So, similarly, yeah. So similarly, when I pass current through a straight current carrying wire, okay, a straight conducting wire, if I pass current, then and sprinkle iron fillings around it, then the iron fillings are arranging themselves in concentric circles with the wire as the center, which means that the wire acts as a magnet, right? Now, in 1864, what happened? The laws obeyed by electricity and magnetism were unified and then formulated by James Maxwell, who then realized that light was electromagnetic waves. So, now let's consider two cases. The first case, that there is a static charge Q1. Now, what do I mean by static charge? Means the charge is not moving. Okay, velocity is zero. The charge is not moving. And a static or a charge with velocity as zero will produce only electric field, right? So, that electric field is given by the formula Q1 by 4 pi epsilon naught R. Okay, so this we will learn in first chapter, that is electric charges and fields. So this electric field produced by this Q1 charge is Q1 by 4 pi epsilon naught R. When placed in an electric field, now this charge Q1, if I say, okay, I am placing one more charge Q, let this blue color dot be one more charge Q over here. Okay, so this will also experience a electric field due to this charge, right? Due to Q1, it will experience an electric field, right? So, and due to that electric field, it will feel a force, right? So, when placed in an electric field, read here, when placed in an electric field, this blue dot, okay, or Q experiences electric field E, and the force on it due to this electric field is given by F is equal to Q into E. This formula. Right. Now coming to case 2. If there is a moving charge Q2, right, means velocity is not equal to 0, right? It is moving charge. So it produces both electric field as well as magnetic field. Okay, so the magnetic force experienced by some other charge. Okay, so this Q, it is producing magnetic as well as electric field, right? Again, if I place some random charge like this blue dot here, okay, and this blue dot will experience electric field as well as magnetic field, right? Electric force due to electric field as well as the force due to magnetic field, right? Now, what is the force due to magnetic field? It is given by the formula F bar is equal to Q2 into V bar cross B bar. Okay, where this blue dot is some other charge Q which is experiencing this force due to the magnetic field. Okay, and B bar is the magnetic field. So here V bar is the velocity of the charged particle, B bar is the magnetic field. produced by that charged particle. Okay, now both magnetic field B bar and electric field E bar are vectors, right? The bar sign only tells us these are vectors. And they both obey the principle of superposition, which means that the field of several sources is the vector addition of the field of each individual sources. This simply in one sentence we can say that if I have many electric fields at the same point due to charge q1, q2, q3 and so on, so the total electric field is just the vector addition of all electric fields, right? Similarly, the total magnetic field is also the vector addition of all magnetic fields. That's all. Now coming to our first main topic of the chapter, that is Lorentz force. So let a point charge q moving with a velocity v bar and located at r bar at a given time t be present in both, okay, electric field e bar and magnetic field b bar. The force on an electric charge q due to both of them is what? See, here we have force due to electric field, right? Which is q into e. And force due to magnetic field is what? Q into V bar cross B bar, right? So similarly, we are just going to add these two forces. Okay, so final force F is equal to what? Q we have taken out common. Okay, so our final force F. Okay, so we have taken Q as common and we have E bar plus V bar cross B bar. Remember, this should be done separately, that is V bar cross B bar should be done separately, and then we need to add that product, vector product, with electric field. Okay, now considering magnetic force, so what is the magnetic force? This, right? F bar is equal to Q into V bar cross B bar. So here, if case 1, my velocity of the charged particle is is parallel, right? These two lines represent parallel. So my velocity of the moving charge is parallel to my magnetic field. That is, if theta is equal to 0 or anti-parallel as well, theta is equal to 180, right? So we have cross product here, right? So what is V bar cross B bar? We will get VB sine theta, right? Cross products gives us magnitude of V into magnitude of B into sine theta. Here you can see this, right? These two steps, V cross B is equal to magnitude of V bar into magnitude of B bar into sine theta, right? So from this, here, if my theta is 0 or theta is 180-degree, sine theta or would become what? Sine 0 or sine 180-degree, right? So this will give me sine 0 is what? 0 itself. So V cross B becomes what? 0, right? Check this. That is, if my V bar is parallel or anti-parallel, parallel, then theta is 0. Anti-parallel, theta is 180. Okay, anti-parallel to B bar, or one more condition, more two conditions are there, right? Or my velocity of the charged particle is 0, right? Means what? My charged particle is not moving on me, it is 0, then there is no magnetic field produced, right? So FB bar, no magnetic field means what? No force due to magnetic field. So my FB bar becomes equal to 0. Case 2. If V bar is perpendicular to B bar, that is theta between them is 90-degree, then the charged particle always takes up a circular path. Now, when the charged particle takes up a circular path, now we know that from our previous classes, that is some 11th or 9th, right? We have learned about the concept of centripetal force, right? It is the force required or force which enables a body, which pulls a body towards the center of the circle so that it moves in a circular path, right? So here that necessary centripetal force is provided by the magnetic force, which means what? Q into V bar cross B bar is equal to mv square by r. So mv square by r is the default formula for centripetal force. Okay, so by substituting here, now what is theta? 90-degree. What is sine 90? 1, right? So here I can directly write q into vb. Okay, here as you can see these two lines. So my qvb is what? Mv square by r. R is equal to what? Mv by bq. Okay, by this formula we get r is equal to mv by bq. V square and v, right? So one v gets cut off and here we'll have qb is equal to mv by r, right? So r we'll finally get it as mv by bq. Now what is mv? m into v, that is mass into velocity, is what? Momentum, right? Which is p by dq. Similarly, from this radius we also have some more terms that can be derived, right? For example, time period t, it is 2 pi r by v, right? 2 pi r is what? Distance by velocity. Time is distance by speed, right? Which is equal to 2 pi m. So here r is what? R formula, we have this mv by bq, right? Substituting that, we will get 2 pi m by bq. Okay, we will get cut off. Similarly, frequency is what? 1 by time period, right? So, ulta for this or reciprocal of this, dq by 2 pi m. Now, angular frequency, when I talk about, it is 2 pi into the frequency, that is linear frequency, 2 pi f, which is equal to bq by m. Now, the next concept we get here is the case 3, that is if charged particle enters at some angle. So the first case was what? Theta is 0 or 180. Second case, theta is 90. Third case, what if it is neither 0, neither 180 nor 90 degree? Okay, some random angle like 60 or 30 degree, right? Then the charged particle takes up some helical path. Now what is a helical path? This kind of structure is known as the helical path. Okay, so this is the velocity, as you can see, velocity vector. This is the magnetic field vector, right? Now what is this pitch? Pitch is the horizontal distance covered by the charged particle in one revolution or one time period. In one revolution, right, or one time period, how much the vertical horizontal distance is covered by the charged particle. Okay, it is the horizontal distance. Now, pitch is actually what? The V parallel component. Okay, now the parallel component of velocity into the time period, okay, which is what? V cos theta into 2 pi m, right? So what is the parallel component of velocity vector with magnetic field? It is this component, right? And if I have theta here, this is cos theta, adjacent side, right? So V cos theta into, what is my t time period? It is 2 pi m by bq, this formula, right? So I will get my pitch ka formula is V cos theta into 2 pi m by bq. Now, coming to the force on a current carrying conductor. So we have the formula F is equal to BQV sine theta, right? It is derived from the same formula, that is F is equal to Q into V bar cross B bar. V bar cross B bar is what? BV or VB sine theta, right? So QVB sine theta or BQV sine theta. Okay, so now we have BQV sine theta. What is V? V is velocity. Velocity is what? Distance by time. Now what is the distance we have? It is L, right? We'll just zoom in a bit more here, right? So F is equal to what? BQ into L by T, distance by time, velocity written as distance by time, right? Now this time is in the denominator, right? So I will take that time in the denominator and I will write my next expression as F is equal to B into Q by T into L sine theta. Okay, instead of L by T, I am taking T in the denominator for Q by T. Now, what is Q by T? Charge per unit time. It is current, right? So, F is equal to BIL sine theta, which is the force on a current carrying conductor. So, here I can write F bar is equal to, in vector form, it is I into L bar cross B bar. Okay. Now, coming to the next thing. So, this is a very, very important three marker, that is Biot-Savart's law. The magnetic field at any point P due to the current carrying element dl is directly proportional to, it is directly proportional to I, the current, dl, the current carrying element, and sine theta, which is the sine of the angle between the current element and the distance from the point P. And it is also inversely proportional to the square of the distance of separation of the current element. This is the current element. So it is the distance between the separation. Okay, this is R. Okay, so it is inversely proportional to R. Square of R. Okay, F is inversely proportional to R square. Okay, so here what we will get, that dB is inversely proportional to r square. So dB directly proportional to I, directly proportional to dl, directly proportional to sine theta, inversely proportional to r square. Right? So I will get an expression called dB is directly proportional to I dl sine theta by r square. So to remove the proportionality symbol, I will add a proportionality constant, right, which is mu naught by 4 pi. Okay, so dB is equal to mu naught by 4 pi into idl sine theta by r square. Now this idl sine theta, we can write it in the vector form as dB bar is equal to mu naught by 4 pi into I times of dl bar cross r bar by r cube. Where what is mu naught by 4 pi? It is the proportionality constant. Okay. Mu naught is the permeability of free space whose value is 4 pi into 10 to the power of minus 7 Tesla meter per ampere. Okay. So I dl bar is known as the current element. You can also remember this. Right. So as our epsilon r can be, or the relative permittivity can be written as epsilon by epsilon naught, and so the permittivity of a medium can be written as permittivity of free space into relative permittivity. Similarly, our permeability can be written as relative permeability can be written as permeability of the medium divided by permeability of free space. So, which implies that the permeability of a medium is equal to the permeability of free space into the permeability of the relative or relative permeability. So, this was the three marker, that is state and explain Biot-Savart's law. Okay. Now, coming to magnetic field on the axis of a circular current carrying loop. This is a 5 marker derivation. Okay, so let there be a circular loop carrying a steady current I. So this is a circular loop carrying a steady current I. The loop is placed in the YZ plane. So this is Y, this is Z, this is X. Okay, it is placed in the YZ plane. Okay, the loop is placed in YZ plane with its center at the origin. Okay, and a radius R. Okay, capital R is the radius. The x-axis is the axis of the loop. Okay, it is passing through the center, so it is axis of the loop. Now we wish to calculate the magnetic field at the point P on this axis, x-axis, right? So let small x be the distance of point P from the center. So this is the point P from the center O of the loop. Now consider a conducting element, a small element of this whole circular loop. I am considering a small element dl. Okay, A and B, as you can see, it is a small element dl of the loop. The magnitude of dB of, that is the magnetic field dB of magnetic field due to dl bar. So due to this small current carrying element, what is the magnetic field? We need to calculate by using what? Biot-Savart's law. So what is that? We will get dB is equal to mu naught by 4 pi into I into dl bar cross r bar by r cube, right? The same formula. Coming to the next one. So using that same formula, we will get, now what will happen? Check for the diagram. Okay, so for this we need the diagram again. That is, what do we have? We have r square is equal to x square plus capital R square. What is capital R square? Capital R square. See, so capital R is this. Using Pythagoras, what they have told, Pythagoras theorem, this hypotenuse, that is small r ka whole square, small r square, is equal to capital R square plus x square, right? By using Pythagoras theorem, that is clear, right? Now, any element of the loop, okay, that is any element of the loop will be perpendicular to the displacement vector from the element to the axial point, right? Any element, if I consider of the loop, of the circular loop, any element if I consider, then what will happen? any element of the loop will be perpendicular to the displacement vector, right? If I consider any element, this is my displacement vector, right? So my displacement vector is always perpendicular to any element of the loop, right? So I have my dl bar cross r bar. I can write it as directly r into dl. Why? Because theta becomes 90 perpendicular, right? So theta becomes 90. Okay, so finally my dB will become what? Mu naught by 4 pi into I dl by r square. Okay, so r will get cancelled. Ideally, it should be what? Mu naught by 4 pi I dl r by r cube. So r cut, we'll get dB is equal to mu naught by 4 pi into I dl by r square. Now next what will happen? What is this small r square? It is x square plus capital R square, right? So dB is equal to mu naught by 4 pi into IDL by x square plus capital R square. Now what is this is what for a small current carrying element. Now what is the total magnetic field for because of the current carrying loop? It is the summation of dB cos theta. Why only cos theta component we are calculating? Because check for the diagram again. See, so this is the cos theta element, right? Now if I have taken AB here, one more if I take element like this here, CD, okay, pay attention, this CD element if I take here, and the similar thing if I calculate from this side, what I will get? I'll get one more component over here as dB sine theta, right? So I can cut off that dB sine theta and the dB sine theta due to the smaller or the region which is below AB, right? This is CD region if I say. So because of the CD and because of AB, both the dB sine theta, that is sine theta components will get cut off, and only the dB cos theta components will get added up. Okay, so we finally have our total magnetic field as the summation of dB cos theta. Now the perpendicular components, as we discussed, dB sine theta of all the current carrying elements cancel each other. So B is equal to summation of, substitute dB cos theta, that is mu naught by 4 pi IDL by r square. Now what is this capital R by R? Check for the diagram again. What is cos theta? It is adjacent by hypotenuse, right? Now if this is my theta, what is my adjacent? Capital R. What is my hypotenuse? Small r. So we have our cos theta as capital R by small r. So finally we get B is equal to mu naught by 4 pi into I capital R by small r cube, and with the summation of dl. Okay, so we want all the current carrying elements, right? Now we just consider small element dl, but we want the whole loop. Now whole loop is what? Circular. So what is the circumference of a circle? 2 pi r. So summation of all the small current carrying elements would become a circle, forming the circumference as 2 pi r. So my B is equal to mu naught by 4 pi into IR into 2 pi r, right? So here we want capital R because capital R is the radius of our circular loop, by x square plus r square to the power of 3 by 2. Okay, so which is equal to mu naught by 4 pi into 2 I pi capital R square by capital R square plus x square whole to the power of 3 by 2. Now if there are n such loops, then we have to multiply the whole expression into n. Okay, and at the center of the current carrying coil, what is our x? Okay, at the center of the current carrying coil, x becomes what? 0, right? So our x becomes 0, and hence our b naught value is what? B naught is mu naught by 4 pi into 2 I pi capital R square by capital R cube. So it will get cut off, and finally we will get B naught is equal to mu naught I by 2R. So if we want the relation between B and B naught, we can take capital R square as common from the numerator and denominator. Okay, here see, if I take capital R square common, okay, capital R as common, what will happen? R to the power of 3 by 2 will come out, right? R square to the power of 3 by 2. So square and 1 by 2 cancel, we'll get R cube. 1 plus x square by r square whole to the power of 3 by 2, which is what? Mu naught I by 2r. This r square r cube cut will get to 2r into 1 plus x square by r square whole to the power of 3 by 2. Finally, we get the relation b is equal to b naught by 1 plus x square by r square to the power of 3 by 2. Okay? Yeah. Now, magnetic field due to an arc which subtends an angle theta with the center. So, an arc which subtends an angle theta with the center. So, we have a circle, a similar circular coil or loop, but now we have a certain angle made by it. Means what? For example, we have this as a circle. Right now, these two are the lines. Right, these two are dividing the circle into what? Two parts. This is 1/4. I can say this is the 3/4 part of the circle. Right, means what? This is theta is what? 90 degree. So this is my small arc making an angle theta with the center of the circle. So this is the thing given there. That is magnetic field. Calculating the magnetic field due to an arc which subtends an angle theta with the center. So B is equal to here what? Mu naught I by 2r into theta by 2 pi. Here your angle should be in the form of radian. Okay, as in 90 degrees should be written as pi by 2. Okay, now which can also be written as mu naught I theta by 4 pi r. Okay, now coming to Ampere's circuital law. This is also very important. Now the closed integral. Now, how to pronounce this symbol? The closed integral of magnetic field is equal to mu naught times the total current passing through the surface. The closed integral of magnetic field through the current element is equal to mu naught times the total current passing through the surface. That is, closed integral of b bar dot dl bar is equal to mu naught times of I. Considering a circular loop with radius r and the direction of magnetic field tangential to the circumference of the circle, we will have b into 2 pi r. Why? Because circular loop, right? dl becomes what? 2 pi r. The whole surface of dl is what? 2 pi r, right? So b into 2 pi r is equal to mu naught times of I. So my magnetic field becomes mu naught times of I by 2 pi r. Now coming to magnetic field at every point on the circle with the radius r is same in the magnitude. In other words, the magnetic field possesses a cylindrical symmetry. Now the direction of magnetic field at any point on this circle is tangential, right? Now here as we considered a circle, right? So the direction of magnetic field at any point on this circle is tangential to it. And even though the wire is infinitely long, right, or infinity, the field due to it at a non-zero distance is not infinity. So if I consider an infinitely long wire, the magnetic field due to it at any point, okay, which is non-zero distance, means what? It should be at some distance, for example, 2 centimeters, right? And at that distance, the electric field is not infinity. Now, to determine the direction of magnetic field, we have the right hand rule. Now, what is that right hand rule? Grasp the wire in your right hand with your extended thumb pointing in the direction of the current. You can do it with me right now. Grasp the wire or take any pen or pencil in your hand and take the direction where the pointer or the pencil lid is there. That is the direction of the current, if I assume. Okay, that is, for example, upward direction. Okay, so grasp the wire in your right hand with your extended thumb pointing in the direction of the current. Your fingers that are curled around will be representing the direction of magnetic field. So this is right hand rule. Now coming to long straight wire of circular cross section. Now this is a long straight wire of a circular cross section with the radius A carrying a steady current I. Okay, it carries a steady current I and the current I is uniformly distributed across this section. Now let's take the first case. That is, our small r is greater than a. What is a? A is the radius of this circle. Okay, a circle is inserted inside that wire. Okay, so this radius of that circle is a. Now if my capital R is greater than a, then now what is capital R? Now here I want to find the magnitude of magnetic field. So I am considering the capital R distance. Okay, capital R is the distance where I draw a circle to find the magnitude of magnetic field. So the current I is uniformly distributed across this cross section, and in the first case we have our small r is greater than a, this case as you can see. Okay, so from Ampere's circuital law, what can we say? B is equal to mu naught I by 2 pi r. So in this case, our B, that is magnetic field, is inversely proportional to the radius according to this formula, right? Now if we see the second case, that is our R is lesser than A. Okay, you can see, have a look at the diagram again. That is, yeah, when my r is inside that small circle, that is small r is lesser than this a distance, then what will happen? Then I have the case of closed integral b bar dot dl bar is equal to mu naught times of I bar. Now why did I take I bar? See, now the current across whole of this wire is I, but we are considering only this circle, right? This circle is not constituting the whole length of the wire, it is a small part of the length of the wire, so I have to consider I dash. Now here, now again what? Dl is what again here? So closed integral is d of dl can be written as what? 2 pi r. B into 2 pi r is equal to mu naught times of what is I dash? I dash is equal to I times of r square plus a square. Now how did I get this? So for a current I, what is the volume of the cylinder that it covers? So if it is like this, right? So for a current I, the volume that it covers is radius is a, right? So it is pi a square h. H is the height. Now for a small spheric sphere or a circle inside that a, what is the current? I dash is equal to pi r square h, right? I dash is pi r square h. So from this I can derive the relation between I dash and I, right? So for I we have pi a square h. So for I dash we have pi r square h. So from these two equations I have my I dash is equal to I into r square by a square. So I substitute this I dash ka value here. So finally I'll get B is equal to mu naught I into R by 2 pi A square. Here my B is directly proportional to R. So here goes the graph for magnetic field or the change in the magnetic field when my R is greater than A and when my R is lesser than A. Okay. So when it is greater than A, R is greater than A, as we saw in the first case, it is B is inversely proportional to R. And if R is lesser than A, then B is directly proportional to R. Now the magnetic field at a point due to current carrying wire. Okay, now we have a current carrying wire. Now if it is a finite length, okay, this is the formula. Now this is for objective part. Okay, so a finite length when I talk about, so this is the angle and I'm from I. Okay, this is a current carrying wire, this is a point P. The distance is represented by this line. Okay, so here this line makes an angle alpha with the top end, beta with the bottom end, and again these two angles are theta 1 and theta 2. Then my magnitude of B is equal to mu naught I by 4 pi r into sine alpha plus sine beta. Only for objective, so derivation is not necessary. Now B is again 4 mu naught by 4 pi into I by r, or mu naught I by 4 pi r into cos theta 1 plus cos theta 2. This is the same formula, just difference as you can see, sin alpha plus sin beta or cos theta 1 plus cos theta 2. Okay, you should remember what are alpha and beta angles and theta 1 and theta 2 angles. Now, if I come for a current carrying wire of infinite length, then what if it is fully infinite and it is semi-infinite, right? Now, what does fully infinite mean? It means that it is infinite from both the ends, that is top end and the bottom end. Okay, so I, and this is the distance r from the point P. So here my alpha is almost equal to beta, which is again almost equal to 90 degree. Okay, because we don't have any finite length to make those angles. Okay, so this becomes 90, and theta 1 is equal to theta 2, which is equal to 0. So my b bar is equal to mu naught times of I by 2 pi r minus k cap. It is in the direction of negative z axis. If I consider a semi-finite, the current carrying wire of semi-infinite length, then alpha is almost equal to 90 degree, theta 1 is equal to 0, beta is almost equal to 0, while theta 2 is equal to 90. So my b is equal to mu naught I by 4 pi r. Okay. Now coming to the force between two parallel carrying current carrying conductors. So this is also an important derivation. Consider two conductors carrying currents I1 and I2 respectively. The magnetic field due to the first conductor, okay, I1 is V1 is equal to mu naught I1 by 2 pi d. Okay, this is the d, okay, distance between these two. Now, where d is the distance of separation between the two conductors. Now, when a second conductor is placed in the magnetic field produced by the first conductor, then it experiences a force, right? It will experience a force of B1. And what is the current carrying conductor? I2, right? And L. So, into L. So, F is equal to what? B1. Substitute the value of B1. Mu naught I by 2 pi d into I2 into L. So what we will get? We will get finally our force per unit length F by L is equal to mu naught I1 I2 by 2 pi d. Or if they ask to find force, then you can find mu naught I1 I2 by 2 pi d into L, taking L that side. Now according to this equation, they may ask us a question. Right? Now what is that question? Define 1 ampere. Okay, so how can we define 1 ampere with this formula? The two conductors are carrying equal currents. Okay, so I square it would become, right, I1 and I1. So, two conductors carrying equal currents separated by a distance of 1 meter, d is 1 meter, experiences a force of 2 into the 10 to the power minus 7 Newton per meter. Then the current passing through the conductor is said to be 1 ampere. We can substitute all these values and check, we will get 1 ampere as our current. Okay, now if the current in both the conductors is flowing in the same direction, then there will be a force of attraction. Here as you can see, I1 and I2 are in same direction, so these two attract each other. If I1 and I2 are in opposite direction, they both repel each other. Okay, now coming to a solenoid. So, as you can see, this is a current carrying solenoid, and we have to calculate the magnitude of magnetic field at its different positions. Now, if I consider at the center, B is equal to, I will get this formula mu naught N into I. Now, what is N? N is the number of turns per unit length. Number of turns per unit length. Number of these turns made per unit length. Now at the ends of the solenoid, this formula changes to half of it. Half of mu naught N I. So alpha is equal to 0 and beta is 90 degree. Here in this diagram, as you can see, this is alpha and this is beta. Right? This is alpha here, this is beta. So this diagram has been derived from this. Considering a finite length, okay, solenoid, and if I consider it to be a cylinder, then B is equal to mu naught N I by 2 sine alpha plus sine beta. Now if my alpha is equal to beta, then B is equal to what? 2 sine alpha, right? Mu naught Ni by 2 into 2 sine alpha. So 2 will get cut off. We will get mu naught Ni into sine alpha. Again from the diagram, what is sine alpha? Check with this diagram. if this is alpha, our sine alpha is what? Opposite, that is L by 2 by hypotenuse, that is L by 2 whole square plus R square the whole root, right? So finally our B would be mu naught Ni into L by 2 divided by root of L by 2 whole square plus R square. Now if our current, as you can see here, the current carrying circular coil behaves like a bar magnet, wherein the direction of current in the coil is clockwise. If it is clockwise, then the phase of the coil acts as a south pole. Here you can see clockwise current like this, it acts as a south pole. You can also guess with the letters here, right? And if the current moves in anti-clockwise direction, the face of the coil acts as the north pole, right? Now, coming to torque acting on the current carrying coil. Now, a rectangular loop carrying a steady current I, as you can see, is placed in magnetic field and it experiences a torque, right? So, it does not experience a net force. Why? Because the forces cancel each other in of opposite directions, right? So, FPQ is equal to FRS. Now, first of all, this is PQ, this is RS, okay? The force acting on PQ is equal to the force acting on RS, okay, which is what BIL sine theta, right? Now, the force acting on PS is equal to the force acting on QR, right? Now, what is the angle made by that two sides? It is what? 90-degree, right? With the magnetic field. So, sine theta is 1. So, we will get these two forces of PS and QR as BIL itself, right? Angle made with the vertical components with the magnetic field is 90-degree. Now, what is the formula for torque? Force into the perpendicular component, right? Which is what? BIL sine theta, BIL into B sine theta. Okay, so this is B. Okay, perpendicular component again B and then sine theta. Okay, now coming to torque is equal to final formula, we get it as BI. Now L into B is what? If this is my length, this is my B, L into B is what? Area, right? So BIA sine theta is my torque, which can also be written as BM sine theta. What is my M? It is magnetic dipole moment, which is having the magnitude of I into A. Okay. Now coming to the next concept, that is circular current loop. Okay. Yeah. So, circular current loop as magnetic dipole. Okay, now we have a circular current loop which acts as a magnetic dipole. Then our B is equal to mu naught I r square by 2 times of x square plus r square whole to the power of 3 by 2. And x is of course the distance along the axis, right? We know the circular coil. Now for x, if the x is very greater than the radius of the circular coil, we can drop the r square from the denominator, right? From down. Now finally what we'll have, this r square is dropped, right? So x square to the power 3 by 2. Now x square to the power 3 by 2 can be written as what? X cube, right? So I'll get B is equal to mu naught IA by 2 pi x cube. And here again what we have, A is equal to pi r square, right? So this is on the axial position. If I talk about the equatorial plane, it will become B is equal to mu naught by 4 pi m by x cube. Now what is m here? M is equal to I into A. So of course this formula will also change, I into A, right? I will get B is equal to mu naught by 2 pi m by x cube. Or if I multiply both the numerator and the denominator by 2, I will get mu naught by 4 pi into 2m by x cube. On equatorial plane, we get it as B is equal to mu naught by 4 pi into m by x cube. Now coming to the final topic, that is moving coil galvanometer. Now a galvanometer consists of a coil with many turns, right? With many turns. It is free to rotate about a fixed axis in uniform radial magnetic field. There is a cylindrical soft iron core which makes, now what is the function of the soft iron core? It makes magnetic field radial and it increases the strength of the magnetic field. Now, when current flows through the coil, a torque acts on it. Okay, when current flows through the coil, a torque acts on it. Now, what is the torque? That is NIAB. Okay, so this torque tends to rotate the coil. Now, if I apply a torque, that is rotation, to this cylindrical, to this galvanometer, okay, so what will happen here? It will experience a turn, right? A torque. So that torque is given. A counter attack or a restoring torque is formed because of this spring, right? If I rotate the spring in one direction, it will have a restoring force in the opposite direction, right? So the spring attached to the coil exerts a restoring torque of k theta, right? We have learned in 11th standard that restoring torque because of the spring is what? Kx. So here it is k theta because the x displacement is what? Theta. Angular displacement is taking place. That balances the magnetic torque. Now, finally, we have that NIAB is equal to k theta, where k is the torsional constant of the spring. The deflection theta is indicated on the scale by the pointer, as you can see this scale, okay, by the pointer attached to the spring. Now finally I get theta is equal to NAB by K into I, which implies that this and all are constant terms, right? Area, magnetic field magnitude, and number of turns by torsional constant. So this tells us that theta is directly proportional to the amount of current. So the angular displacement is directly proportional to the amount of current passed through the coil. A galvanometer is a device used to sense current in a circuit. Okay, and here you can see this is uniform radial magnetic field as we discussed. Okay, now, coming to conversion of galvanometer into ammeter and voltmeter, this is also a very important question. How to convert galvanometer to ammeter or how to convert galvanometer to voltmeter. First, what is an ammeter? Ammeter is used to measure the amount of current in a circuit, and hence there should be low resistance. Now ammeter is used to measure what? Amount of current, right? So if I want the quick flow of current, resistance should be low, right? So a galvanometer can be converted into an ammeter by connecting a resistance, a low resistance in parallel. When we connect a resistance in parallel, the total resistance of the whole circuit decreases, making it an ammeter. So now, see, if we are connecting in parallel, what is same? Potential, right? The potential V, which is equal to IR, in parallel combination is same through the each resistor. So what will happen? Now V is what? I into R. Through this connection, I is what? Ig into G. G is the resistance, right? Resistance to the galvanometer. So Ig into G is equal to what? Now the second part you see, second path of current. That is I minus Ig. If this is Ig, this is I minus Ig, right? So I minus Ig into S, right? So this S is what? S is known as the shunt, which is a low resistance connected in parallel to a moving coil galvanometer in order to protect it from large currents. Okay, it is a low resistance that is connected in parallel to a moving coil galvanometer in order to protect it from large currents. So the formula for this shunt can be derived by this, that is Ig into G by I minus G. Now what is the resistance of an ideal ammeter? If I consider an ideal ammeter, its resistance is 0 because there is full flow of electric current. Now if range is increasing by n times, so this we will see after studying voltmeter as well. Now, a conversion of galvanometer to voltmeter. A voltmeter is used to measure the voltage across the circuit, and so V is directly proportional to R, right? So resistance should be high. So the galvanometer is converted into a voltmeter by connecting a very high resistance in series. So resistance in series is what? The total resistance increases, right? We can directly, the total resistance we can say G plus R. While here in parallel, total resistance is what? 1 by R is equal to 1 by G plus 1 by S, right? Parallel. Resistance in parallel is lesser than the total resistance in series, right? So the current ig here, now in series combination current is the same through each resistor. Okay, so what will happen, ig is the current through g as well as the resistor r. Okay, with resistance r. So my v is what, again v is I into r only, but what is my total resistance of this voltmeter? It is g plus r. So ig into g plus r. Okay, now if I take ig this side, v by ig is equal to g plus r, and finally we get the value for this high resistance that is need to be attached in series, which is v by ig minus g. The resistance of an ideal voltmeter is infinity. Now we have one more term. If we that the range is inversely proportional to sensitivity. What is sensitivity? As we saw, a galvanometer is used to sense the current, right? So if I increase the range of the current, sensitivity decreases. So now let's see, if the range is increasing n times, then what will happen in the case of ammeter and voltmeter? First case is in the case of ammeter. 1/nth of the total current should pass through the galvanometer in case of ammeter. So what will happen to decrease the current? Connect resistance in parallel. Okay. So what will happen? Ig into G is equal to I minus Ig. Again the same equation. Here again what we'll do, we'll take Ig this side, we'll take S that side. So G by S is equal to I minus Ig by G, which is equal to I by Ig minus 1, right? So the current we want through the galvanometer is what? We want our galvanometer ka current Ig should be equal to 1/nth of the total current I, right? We want to decrease the current. So our I by Ig can be written as what? 1, right? Ig taking that side and going that side. So I by Ig can be written as what? N. So I can write, substitute N here, my G by S is equal to N minus 1 and S is equal to G by N minus 1. So this is one more formula to calculate the shunt resistance that is to be calculated, to be attached in parallel with the moving coil galvanometer. Now, if the range is increasing n times, what to do with the voltmeter? We have to increase the range by n times. A resistance R should be connected in series, right? For a voltmeter, we would have to connect a resistance R in series. Now, what will happen for a voltmeter in series, right? So, series means what? Voltage is different. So, my final voltage is n times of the voltage through the galvanometer. Final voltage is n times the voltage through the galvanometer. That is V is equal to n times of Vg. So what is my V? As we calculated in this step, what is our V? V is equal to Ig into G plus R, right? V is equal to Ig into G plus R. So I will substitute that. And what is my Vg? That is only the potential through the galvanometer. It is G into Ig, right? Only this part you see. G into Ig, right? I into R, that is G into Ig. So what will happen? Ig into R plus G is equal to my n times of Ig into G. So I can cut off Ig from both the sides. I will get R plus G is equal to n times of G. R is equal to Ng minus G. So the final value of this resistance that is needed to be connected in series can also be calculated with the formula of R is equal to n minus 1 times of G. So with this concept, we are done with the chapter known as moving charges and magnetism. Thank you.